So our speaker today will be two speakers. First, Eugenia Ellis will speak, and then Emanuel Rodríguez Cirone will speak on a joint work whose title you can see on the screen, Algebraic KK Theory and the KH-isomorphism conjecture. Please, Eugenia, go ahead.
Okay. Well, thank you for giving us the opportunity to tell about this present theorem that we have. And I'm going to talk about it. Then this is about algebraic KK theory and the KH-isomorphism conjecture. Then what we do is to relate Davis-Lück homology with coefficients in Weibel's homotopy K theory to the equivariant algebraic KK theory. How? Using homotopy theory and adjointness theorems. What we do is also to express the left-hand side of the assembly map for the KH-isomorphism conjecture introduced by Bartels-Lück in terms of equivariant algebraic KK groups. Then this is the whole story. I'm going to give an introduction explaining all the ingredients. Then I'm going to state the main theorem, and with Emanuel, we are going to explain the proof of the main theorem. I'm going to explain what is equivariant algebraic KK theory, what adjointness theorems in algebraic KK theory means. I'm going to present the spectra representing algebraic KK theory and what is the KH-isomorphism conjecture. Then algebraic KK theory was introduced by Guillermo Cortiñas and Andrés Tom in order to show how methods from K theory of operator algebras can be applied in a completely algebraic setting. Then in this talk, L is a commutative ring, and Alg is the category of algebras over L. Then algebraic KK theory can be viewed in simultaneous with Kasparov KK theory. In what sense? Kasparov KK theory is a bivariant K theory on the category of sister algebras. That means that there is a triangulated category called KK, and there is a functor from the category of sister algebras to this category KK, which is stable with respect to compact operators. That means that if we have a sister algebra and we take the stabilized sister algebras by compact operators, we have these two sister algebras identified in this category. This functor is continuous homotopy invariant. That means that if we have a sister algebra B, we identify it with the sister algebras of continuous function from the interval to B. And this functor is split exact, and this functor is universal for these properties. On the algebraic side, we have a bivariant K theory on the category of algebras. We have a functor from the category of algebras to a new category called KK also, whose objects are the algebras and the morphisms are the KK groups. And this functor is stable with respect to matrices. That means that we identify these two algebras in this category. And we have a polynomial homotopy invariance. That means that every algebra B identifies with polynomial algebras in KK. And we have this functor is excessive for some extensions. And then this functor is universal for this property. Then the other important property is that if in Kasparov KK theory, if we put the trivial sister algebra in the first input, we obtain the topological K theory of the sister algebras A. And in the algebraic KK theory, if we put the trivial ring, which is L, we obtain the K homotopy theory defined by Weibel of the algebra A. Then equivariant algebraic KK theory was introduced by myself, and it's an equivariant version of the algebraic KK theory. That is a bivariant K theory on the category of G algebras. Then we have a functor from the category of G algebras to a new category KKG, which is G stable, which is a equivariant version of matrix invariance. Is polynomial homotopy invariant, satisfy excision, and also is universal for this property. And this in this column we have the corresponding properties in Kasparov KK theory. And finally, there is a theorem in Kasparov KK theory called Grignard theorem, which says that if G is compact, then KKG of CA is the topological K theory of the cross product G with A. And in the algebraic side, we have a version, an algebraic version of this theorem. The hypothesis is G is finite and the order of G is invertible in L. Then if we take this KK group, we obtain the homotopy K theory of the cross product. Then, as I said, okay, this is algebraic linear theorem. Is a little bit more general. In the previous slide, there was B with the trivial algebra, that holds in general version. In this general version, we need that G has to be finite and with order invertible. Then we have these two groups isomorphic, and we have an isomorphism that we are going to use later. And we also have a adjointness theorem between the in algebra and the induction algebra and the restriction algebra. Then if we have a subgroup of G, H, then we have an isomorphism from this group and this group. That means that this functor, induction functor, is left adjoint to this. Okay, another ingredient that we need is the category of spectra. We are going to work with simplicial spectra because we need a property of the category of simplicial spectra. And I recall what it is. Simplicial spectra is a sequence of simplicial sets such that together with morphisms from this simplicial set to this one. This morphism and called bonding maps, and the morphisms in the category of the spectra are sequence of morphisms of simplicial sets such behaves well with the bonding maps. That means that this diagram commutes. Then what we need in this work is a spectra. We need spectra representing algebraic KK theory and equivariant algebraic KK theory. Then for 2L algebras, we are going to consider this spectrum, which was defined by Garcuja in 2014, such that if we take the stable homotopy groups of this spectrum, we obtain algebraic KK groups. And later, Emanuel defined the spectrum representing equivariant algebraic KK theory. Then it's a spectrum such that if we take stable homotopy groups of the spectrum, we obtain equivariant algebraic KK theory. Then we are going to work with that also. Then, what is the language of isomorphism conjecture in the sense of Davis-Lück? Then we have a group. We have the orbit category of this group, whose objects are G mod H, where H is a subgroup of G. And morphisms are equivariant maps from here to here, and the action of G is the multiplication at the left side. And given a functor from the orbit category to the category of spectra, Davis and Lück define an homology, a equivariant homology on the G simplicial sets. This is a simplicial version of this homology theory. Yeah, I'm not telling the whole properties that this homology satisfies, but it's what we need in a equivariant homology theory. Then, if we have a family of subgroup of G, we consider the classifying space of G associated to this family. This family is closed by taking conjugation and subgroups, and satisfies that if we take the fixed points of a subgroup H, this space, this simplicial set is contractible if the group belongs to the family, and is empty if the group do not belong to the family. Then, okay, we have the projection of this simplicial set to the trivial one, and the assembly map associated to this triple is this homology applied to this projection, and we have this map. And the isomorphism conjecture for this triple is true if this map, which is a map of spectra, is a weak equivalence. If this map is a weak equivalence, then the isomorphism conjecture is true. Then the KH-isomorphism conjecture is a particular case, it's a particular conjecture in this set. Then F is a family of finite subgroups. And the spectrum consider here to define the homology is this one. This is a ring associated to this thing, which fix the problem that if we take, for example, here, if we take a functor from A to the cross product, there is not a functorial property, but this thing fix that problem, and then this is KK equivalent to this one, to this algebra, yeah. Then this spectrum, which represent algebraic KK theory, satisfies that if you take the homotopy groups, Then we have the KK groups of these things, which coincides with the K-homotopy theory of the cross product H with B. Then the KH-isomorphism conjecture, a group satisfies the KH-isomorphism conjecture if the assembly map is a weak equivalence. Well, yeah. Here we have coefficients in of course. Okay, then what says the main theorem? Then what we do is to write the left-hand side of this assembly map in terms of equivariant KK theory, equivariant KK groups. Then our main theorem says that, okay, if we have a group such that the order of every finite subgroup H of G is invertible in L.
Wait. The Barshi is asking whether on this slide G is an arbitrary infinite group. And I think so. I think the answer is yes, but
yes. Sorry, I didn't see that. In what in general, in what generally does Green-Yell theorem hold for KK is in the general the hypothesis is when G is finite and the order is invertible
in a ground ring.
Yeah. There is a dual. There is could be a dual version. This is the analogous of the compact version, but there is also a co-compact version, I think, and the dual version could exist, and that's was one thing that I put in the freezer and never think deeply. And in this slide, is G an arbitral infinite group? Yes, it's a group. It's arbitrary. Yes. In the main theorem, in this one, what we need here.
What I meant was in the previous slide, is it possible that you're using this Green-Yell theorem somewhere? So in this note that you have KK star L of R of B cross with G mod H is KH star B cross product with H. How do you get from one to the other?
This one.
Yeah, this has nothing to do with Green-Yell.
Yeah.
Okay.
This is a result of Willy and Andreas Thom.
Okay.
This is
no, but this is no. Our result is that. So go. Where were we? Yeah. So R of B cross G mod H is a ring that is equivalent, has the same K theory, KH theory, say, as the category B cross G mod H, which instead, in turn, is Morita equivalent or equivalent to the category B cross H. So on the left-hand side, you have KH of this R ring, which has the same KH as the cross product. And this is for any H, doesn't have to be finite or anything.
Okay.
So it's a matter of Morita equivalence if you want.
Right. Okay. Thanks.
Yeah. Then the main theorem, we have an arbitrary groups, but we need that for every finite subgroup, the order of this subgroup is invertible.
It is important to point out that next to the word main theorem in the parentheses, what is next to the E is a comma and not a dot. E is for Ellis, not for Emanuel. If it were a dot, it would be.
Yes. Then, okay. Then the left-hand side of the KH-isomorphism conjecture is equivalent to the thing that the colimit here runs into the G finite subcomplexes of this space. G finite means every G, if X is a G space, then there is G cells that are the form of this, are the form, I like this, and G fin, this X is G fin if this H is it's finite. Then, for example, if G is not finite, then the point is not G finite space, because here you have to have G. The point, for example, if you take the simple, the n simple here, you need G mod G, and this is a G space if G fine space if G is finite. Then this is what I mean. Then, okay. Then we are going to explain how we prove that. Well, we are going to use the adjointness theorem that I mentioned, the induction and restriction isomorphism, which is the thing, and the Grignol isomorphism, which is here. Then H is finite, then we can apply Grignol, and here we don't have any restriction in the group. Then what we do is to consider these morphisms at the level of spectra, that Emanuel proved that this morphism can be lifted to at the level of spectra. Then, if we consider orgy spectra here, this is the spectra which is used in the KH-isomorphism conjecture. Here, this spectra. We would like to identify it with this spectra, which only is defined when H is finite. Then this F is an orgy finite spectra. Okay. Then we are going to relate these things using homotopy theory. Then how we do that? How we prove this equivalence? Then first, we are going to use this F, this orgy fine spectra F, and we express the homology, which is if we have F is an orgy finite spectra, then if we take the Davis-Lück homology with coefficient in this, we obtain a homology on the G-fin complexes to spectra. Then we work with this spectra, and we write this homology in terms of KKT. And as a second step, we relate these two homologies, the one with coefficient in E and the other with coefficient in F. And then we obtain the final result. Then I'm going to explain the first part and leave the second one to Emanuel. Then how we express this homology in terms of KKT. Okay, first we construct morphisms of spectra from here to here that are natural in the space E. This involves a lot of technical details using explicitly the spectra KG. But once that we have construct these morphisms, we can use it in order to show that we have a weak equivalence from here to here. Then for every J-fine complex, we can write this complex as the colimit of these finite subcomplexes. Then the morphisms that we are used are the colimits of the alphas defined above. Then we prove that this is a weak equivalence from here to here. Then we obtain what we want in this step. How we prove that? We prove that this is a weak equivalence in 4 steps. Then we prove that this map is a weak equivalence for every G-fine finite X. And we start with the simplest simplicial set, which is by construction. Then actually in this construction, alpha X is a weak equivalence in this case, almost. For this step, for G mod H times delta N, we use homotopy invariance of KK. Then we obtain, because in order to show that this is a weak equivalence, we have to prove at that level of groups or level of group of KK. We prove that this third step, which is an union of things like the second step, using that the homology and the KK is additive. And the last one, in the general case, we proceed by induction in the dimension of X. And what we use that here is Mayer-Vietoris property in the homology theory and escission property in the side of KKG. We start from a Milnor square, and then we use 5 lemma and obtain that we have a weak equivalence. Then this is the first part. We write this thing in terms of KKG. Then now it's time to Emanuel.
Euge, I think you have to stop sharing your screen in order. Thank you. Okay, so I will talk about this second step in the proof of our main theorem, which is proving that the homology with coefficients in F is weak equivalent to the homology.
Well, for some reason, the sound looks like with a lot of echo.
Oh, and maybe because there's a lot of echo here, maybe I can try to change room.
No, maybe the if you had a mic next to your mouth, you.
Yeah, but I don't have one.
Okay.
I could try to change room if that solves the problem.
There.
Okay, so then I will talk about the second step in the proof of our main theorem, which is showing that the equivariant homology of G fine complex Y with coefficients in F is weakly equivalent to the homology of Y with coefficients in E. F and E are the spectra that you can see here. So we have this theorem that says that if the order of every finite subgroup of G is invertible in the base ring, and A is an algebra and B a G algebra, then these two OR-G fine spectra, E and F, are connected by a zigzag of OR-G fine spectra that induces an isomorphism upon taking homotopy groups. So how do we prove this result? Well, if we take homotopy groups, here we get KK groups, here we get KKG groups, and we know that both groups are isomorphic because of the adjointness theorems that Eugenia mentioned some minutes ago. So combining the adjointness theorems, we get a composite adjunction between these two functors, and we want to lift this adjunction isomorphism to a weak equivalence of spectra. we have explicit descriptions of the unit and co-unit of this adjunction. So we have an explicit description of the adjunction isomorphism. So the adjunction isomorphism, here we have the homotopy groups of E, sorry, and here we have the homotopy groups of F, and this the adjunction isomorphism is this composite. Here we are applying one of the functors, the left adjoint, and the rest is the counit. So in KK, the counit of this adjunction is represented by this composite here. So that the adjunction isomorphism is obtained upon applying the left adjoint and then composing with the counit. This morphism here is induced by an algebra homomorphism. We didn't give the explicit construction of R, but this involves taking a quotient of a tensor algebra, so that this construction doesn't commute with tensor products, but we have a map in one direction, and that's the map we are using here in the vertical morphism. That map can be proved to be a KKG equivalence, and that's why this is an isomorphism. And here, zeta G mod n, that's a functor of linear categories. Here we are considering this algebra as a category with only one object. So what we want is to replace this zigzag that we call the primitive zigzag by zigzag of orgy-fine spectra. The problem with this zigzag is that here we have an orbit space, here another one, and here another one. It is not clear how to consider this thing as a functor from orgy-fine to spectra. So this is, it is not clear how to consider this as an orgy-fine spectra. The same happens with this one here. So we want to replace this zigzag by a new zigzag of orgy-fine spectra that induces the same morphism in the stable homotopy category as this primitive zigzag. So the first thing, we'll concentrate our attention on this zeta G mod n. But before, we will fix some notation. To ease notation, we will call, we will write O for the category orgy-fine, and the objects of O, that is the orbit spaces corresponding to finite subgroups, will be denoted by letters R, S, and T. So the primitive zigzag with this notation, it looks like this. Here we have the KKG equivalence, and here we have the morphism zeta. Let us concentrate our attention on zeta T. If we take a morphism F in orgy-fine, a morphism F from an orbit R to an orbit S, we have a commutative square like this. So here we are treating these three variables as separate variables, so that we could call this L T of SR, so that this spectrum depends covariantly on R and T and contravariantly on S. So in this diagram, T is fixed and we move S and R. So this would be LT of RR, and this would be LT of SS. And the commutativity of this square makes us think of a coend, because the coend is the thing that we can put here, the object that we can put here, that receives morphisms like this zeta R, and which is universal with that property. So the coend is something that sits here, receiving morphisms from these ones, and for each commutative square, there will be a unique morphism from the coend, making the whole diagram commute. For technical reasons that I will try to explain, we will take coends over a slice category. So let us explain that. Write B of OSP for the category of functors from the opposite category of O times O to spectra. This is what we will call bifunctor on O. So let L be defined in this way. That's what we were doing here. We are talking about this L. And so that for each T, L sub T is a bifunctor on O. And that bifunctor depends covariantly on T. So we fix T and we let O over T be the slice category over T. So the elements of this slice category are morphisms whose range is T. For example, an object could be a morphism alpha from R to T, and a morphism in the slice category from alpha to beta is a morphism from R to S, making this triangle commute. We have a forgetful functor from the slice category into O. And we can restrict a bifunctor along this forgetful functor. This is what this functor does. It picks a bifunctor on O, and it restricts both coordinates to the slice category along the forgetful functor. So with these definitions, we can take a look at this square one more time, and the square now looks like this. So the outer square here is exactly the square in the previous slide. We are just adding notation, and we can think what we are doing is we are restricting this bifunctor LT to the slice category over T. So we can take coend of that, and there will be a unique morphism from the coend into this thing, a morphism that we will denote zeta T. Okay, so we would like to prove that this morphism is natural in T. So we want to prove this result, this lemma, but first we have to explain in what sense this depends covariantly on T. So that that problem is addressed by the following lemma. If we have a bifunctor V depending covariantly, a family of bifunctors depending covariantly on O, then the assignment that maps an orbit space T to this coend over the slice category over T defines an O spectrum. And moreover, this construction is natural in V. So using this lemma, this the domain of zeta T depends naturally on T, and it makes sense to say that this morphism is natural.
One question. The second lemma, does it matter that the target category is spectra? Or
no, it holds for any category where you can take coends.
Okay.
For any complete category, it holds. No, this is this lemma is purely categorical. The proof. Okay, so so far what we have the primitive zigzag that has the problems that these are not orgy-fine spectra. We want to replace it by a zigzag of orgy-fine spectra. So we can call this M sub T. We can call this L sub T. And we have we found an analog of this morphism zeta, which is a morphism of orgy-fine spectra. So this green arrows will mean that the morphism is a morphism of orgy-fine spectra, that it is natural in T. So we have taken care of this morphism, and we found an analog that is natural in T. We want to do the same with the rest of the morphisms in the primitive zigzag. So what can we do with this morphism psi? This morphism is induced by an algebra homomorphism. So we have a morphism from L to M, which is induced by an algebra homomorphism, which is moreover a KKG equivalence. And this gives us a morphism from L to M in the category of bispectra, bifunctors that depend covariantly on orgy-fine. So we could apply this lemma. We have a morphism in this category. The morphism psi is a morphism in this category. If we take object-wise coends, we would get a morphism here. The problem with this is that taking coends, in general, it does not preserve weak equivalences. So even though object-wise we have a weak equivalence, upon taking coend, we may not have a weak equivalence anymore. So instead of taking a regular coend, we would like to take a homotopy coend. And for that, we will introduce a model structure in the category of bifunctors. Instead of taking coend, we will take homotopy coend. So let's see be a model category and gamma be a small category. We can consider two model structures on the category of functors from gamma to C. The injective model structure, in which cofibrations and weak equivalences are defined object-wise, and the projective model structure in which fibrations and weak equivalences are defined object-wise. Well, then we have this proposition by Lück that says that if C is a combinatorial model category and gamma is a small category, then both model structures, the injective and the projective, exist and are again combinatorial. A combinatorial model category is a cofibrantly generated model category that it is locally presentable. This last condition is a condition on the underlying category that we do not want to get into that details. We are only interested in the fact that the category of simplicial spectra is combinatorial. So both structures exist when C is spectra. So we have this morphism psi in this category. That's object-wise a weak equivalence. We want to take the homotopy coend of that morphism. And then we have this theorem by Arkikov and Ørsted that says that if this structure exists in the category of bifunctors, if this model structure exists, for example, if C is the category of spectra, then taking coend is a left Quillen functor. And this is good because if it is left Quillen, we can derivate it and we get a model for the homotopy coend. We can take a cofibrant replacement in this category, then take coend, and that would be a model for the homotopy coend. Since we can take functorial cofibrant replacements, that would give us a natural way to construct homotopy coends. But there's a problem, which is that we are taking coends indexed by different categories, because we restrict L sub t, we restrict it to the slice category and then take coend in the slice category. So we would need to work with different cofibrant replacements in this corresponding to these different categories. So that seems complicated, but if we show that restricting a bifunctor is a left Quillen functor, we can take a cofibrant replacement here, and then if restriction is left Quillen, the restriction of something cofibrant would be cofibrant, and then we could use that as a model for the homotopy coend, and that holds. That is part of our work with Eugenia, restricting both coordinates of a bifunctor from O to a slice category along the forgetful functor is a left Quillen functor. So in this way, we solve this problem of taking homotopy coends. We take a cofibrant replacement in this category, and since restricting and taking coends are left Quillen functors, we have a model for the homotopy coend of this morphism. Okay, so far we have taken care of this morphism and replaced it by zeta t, the green zeta t. Then we have taken care of this because we can take its homotopy coend. Here, this arrow going up is the natural morphism from the homotopy coend to the coend, which is the morphism when you take covariant replacement, a covariant replacement factor Q comes with a natural transformation from Q to the identity of your model category. So this would be induced by Q. And then we have here the homotopy coend. Since it is an homotopy coend, it preserves weak equivalences, and this is a weak equivalence. So we still have to take care of this first morphism. Okay, we want to think of this morphism as a part of a morphism of bifactors. So if we treat these variables as separate variables, and we tensor with this algebra, we have this first morphism, but we would like to have a dotted arrow like this, because we want to think of a morphism of bifactors. So in order to be able to define this dotted arrow, we would need a morphism from S to T. We would need this in order to be able to define this dotted arrow. And this justifies in part our choice of the slice category as indexing categories. So if we work with bifactors on this category, on the slice category, we are able to define a morphism of bifactors like this, like the orange one, and then we can take coend and we can define a morphism here. I'm not giving all the details because this is really technical. Here, for example, we have an homotopy coend. Here we don't have homotopy coend. Well, we have to do something there, and moreover, this orange morphism is a morphism of O over T. So for each fixed T, we have a functor, a bifactor on the slice category, and we are taking coend of that bifactor. But then we move T, and we want it to be natural in T. We can't apply this result here, because this result, in order for this result to hold, you have to take coend of something that is the restriction of a bifactor on org-fine. This is not the case here. I mean, it is the case for the objects, but not for the morphism. In order to define this orange morphism, you have to define it at this level. So the naturality of this arrow is not immediate from what we have said before. You have to prove it in particular for this arrow. And then once you define this orange arrow, the last observation is that this coend is equivalent to this, which is our E of T. And why these two things are weak equivalent? Well, here we are taking coend of a bifactor that is constant in the contravariant variable, and such a coend is the colimit of the corresponding factor. So this coend is actually a colimit of this factor, and we are taking colimit over a slice category, which is a category that has a final object. So the colimit over this category is just evaluating at the final object, and that gives us this equivalence, this isomorphism, in fact. Well, that's all I had to tell. We managed to replace each of these morphisms by morphisms of all G-fine spectra, and in that way we get our desired zigzag of all G-fine spectra. That is all.
Okay, thank you very much. Are there any questions? If not, I'll ask this orange map. You say it takes it's not obvious that it is natural, but is it obvious that there is a map at all, given that one, I mean, you cannot go from the ordinary coend to its homotopy coend. The natural map goes in the opposite direction, right? So, I mean, is it also very technical to actually define a map in this direction?
Yes, it is technical. I can show you. We are finishing our preprint. I can show you the final diagram. It is technical because
but now the only thing I see is the word Emanuel in the full screen.
Sorry.
So maybe Eugenia is waving the piece of paper. Maybe I should switch to her. Yeah. So you hand this.
Oh, that thing. That is that I was looking for that.
That's the orange map, where that is some of the arrows there, a composite of arrows that show up there, I suppose.
Yes, I can share.
Mm-hmm. There it is.
So here we have the morphism psi. That is the one induced by taking out the tensor product of the R. So this is the weak equivalence. Here you have the homotopy coend. That's this Q is the cofibrillant replacement of bifunctors. So this Q bar and this Q are cofibrillant replacements. Q is the natural transformation that comes with Q, and Q bar is the natural transformation that comes with this Q bar. Here J is the name we put to this functor. Oh, sorry, this functor. J is a functor from org-fine into spectra. It only depends on one variable T. It's a covariant functor. So this delta is considering the functor J as a bifunctor, adding a contravariant variable, a constant contravariant variable. So J is a functor, delta J is a bifunctor induced by J, which has a constant contravariant variable. So you also have to take a cofibrillant replacement of this functor J in the category of functors from org-fine to to spectra in order to be able to get rid of the covariant replacement. And moreover, you have to show that this functor, sorry, my computer will, I'm not connected to that. Just a minute, please. Okay, I'm here with echo again, but
Okay.
and this corner, upper left corner, what we have is j of t, and then you have to take a covariant replacement of that functor in the category of functors, and that is needed to get rid of the homotopy coend. And you have to prove also that this functor, which is the left adjoint to restricting the contravariant variable, you have to prove that this functor is a left Quillen as well. So here, from this Q bar to the top, everything is part of this the final step, of which I did not give the details. So it is technical, yes.
Yeah, I can see. It is very technical. Very, very impressive what you've done.
Okay, thank you.
So, are there any more questions, or shall we stop the recording? Okay, let's stop it then.